I wanted to go over with you recursive and explicit equations for our three functions that we've been looking at. Now, when we're looking at a recursive equation, remember that our recursive equation, it tells us the next value from the previous term. So that's what our recursive is. That's what this notation means here. This is the next term, the previous term. Okay, so if we take a look here at our table, now we know that we can find the first and second differences to help us find out what kind of function it is. So here, this is going up by 4, up by 4, up by 4, up by 4. So when it's going up by 4, that means that this is linear because the first difference is the same. Okay. Now, when we want to find our equation, what we always look at, we always need to say what our first term is. So here, our first term is with our x value of 1. So that's our first term. And we would say that f of 1 is 10. So down here we've got f of 1 is 10. So then the next thing that we're going to say is we get the next term by doing the previous, and then we're adding whatever our common difference is. Okay? So in this case, we have our common difference, which is our first difference, which is 4. So in our equation, we're going to do f of x equals f of x minus 1 plus 4, where this is talking about the common difference, and then that we have put what our first term is. Okay? And that is what we have for linear. Now, if we look at the next one, if we find our first difference, this is going down by 5. Make sure if it's going up or down that you notate with your negative signs if it's going down or positive signs if it's going up. Okay? Well, notice the first difference is not the same, so I know this one is not linear. So then I'm going to look at the second difference. Well, here this is going up by 2, up by 2, up by 2. Right? So that means that our second difference is the same. If the second difference is the same, we know that this is quadratic. This is our new one that we've been working with. Okay? So if our second difference is the same, we know it's quadratic. Okay? Now, when we go to write it, again, with our recursive, we say what the first term is. The first term is the x value of 1. So in this case, our first term is f of 1 is 3. Okay. So once we've got that, we're going to look at how we get the next part. Now, this is saying the next one is doing the previous and then plus some linear amount. Remember, your quadratic is always adding a linear portion to it. So the m is your second difference. The b is what you add to get to the y-intercept. Okay? So in this case, if we look, our second difference is going to be, well, that's a bad color because you can't tell. Our second difference is going to be the 2. Okay? So that's going to be our m. So we're going to have f of x equals f of x minus 1 plus 2x, and then we've got something, right? Where this is our second difference. Now, if we go to look, we've got the way that we're getting to our y-intercept. Notice this is our y-intercept here. So notice I added a negative 3, or I subtracted 3 to get to the y-intercept. So this negative 3 is going to be what we're doing to get to the y-intercept, which is our b value. So then we're going to have plus a negative 3, which will just be a minus 3. Okay. And that's how we can get our recursive for quadratic. Now, for exponential, I've got two tables here. I wanted to, well, I guess I already blew it that it's exponential. This next one is exponential. There's two patterns that you can see in a table. You've talked about one before, and you may or may not have talked about this second one. So I want to make sure that you understand that there's a second pattern that sometimes works. So if we look at this first one, we've got that this is, we're multiplying by 3, we're multiplying by 3, we're multiplying by 3, we're multiplying by 3. And that's how we can tell. So this is exponential. Sometimes we refer to this as geometric. Sometimes when it's linear, we also refer to it as arithmetic. So anytime that you multiply or divide by the same number to get to the next, then you know that it's exponential. Now, there is a second pattern that sometimes happens. This second pattern does not work with all exponentials. But had you gone on autopilot and found the first and second difference, so your first difference here, these are 64 apart, 128 apart, 256 apart, 512 apart, and then you went and did the second difference because those are not the same. So you get 64, 128, 256. Well, if you notice, these numbers are the same. The 64s match the 128s, the 256, and then the next one would be 512. So there is a pattern that works, again, only with some exponentials, where the first and second differences match, then you also know it's exponential.
I wanted to show you two more examples of how you can see exponential tables if you look at the first and second differences. So if we look here, this is 256 apart for our first difference, and it's going down. This is going down by 128. This is going down by 64. If we look at the second difference, this is going down by 128. This is going down by 64. So if you notice, we've got that this matches, the 64s match, and then, well, negative 64, and then the negative 128s match. If we look at this one over here, this is 3 apart, then 6 apart, then 12 apart, then 24 apart. And if we check the second difference, this is 3 apart, then 6 apart, then 12 apart. So notice you've got the 3s match, the 6 match, the 12 match, and then the 24 would be the next one. So on this one, notice that we're going down, right? And so these two don't match, it's the bottom ones that match and then go up, as opposed to this one where we're going up and then the top ones match and then the bottom one is missing the next one because we don't have that next piece of information. Although we could find it. So that is how you can look at exponentials. Now, this doesn't work for all exponential tables, but for some exponential tables. So if you went in habitual mode and just started finding the first and second difference, there is a way that you could potentially find it. If it doesn't work where the first and difference are the same, and the first difference isn't the same and the second difference isn't the same, then I would go and check and see, is there a common ratio?
Okay, we're not going to find the equation for this one, so the equation for this one is going to be with the left table. Okay? When we're finding this, again, we still need our first term. So if we find our first term, we have f of 1 is 9. Right, so that's going to be our first term that we're going to write here. Okay? So our f of 1 is 9. Okay? So then we find our recursive by saying that we take the previous term and then we times by the r. That's our common ratio, which is this part here. So I'm just going to say f of x equals f of x minus 1, which is the previous, and then times by your common ratio, which in this case is times by 3. So then we've got that this times by 3 matches the r, which is the common ratio, which goes right here. Okay? So that's how you can find that. If you did this way, I would go back and find the common ratio after I've realized that it's exponential or geometric, and then use this same method to get there. Now, sometimes you want to have an explicit equation. Okay? So if you want an explicit equation, that's when you calculate any term instead of just the previous one. Okay? So here we have looked at figures to tell if they are linear, quadratic, or exponential. So here are some examples. So notice on this one, I'm going to forego having you count, but there's 5 in this first figure, 9 in the second one, and 13 in the next one. So notice we're going up by 4 and up by 4. Or the part that's changing is that I've got these 4 extra, these 4 extra. Okay? So we know that this is linear because it adds the same amount each time. Okay? Now, there's two different ways that we can look at linear. You may have learned either one of these ways. Both of them I'm fine with. So this one, you're taking your first term and then your common difference, and then you times it by x minus 1. Okay? You may have learned this one last year. You may not have learned this one last year. I'm going to show it to you so that you can see. I haven't looked at this one with you this year yet. Okay? So f of 1, that's our first term, so that's 5. So that means that this 5 is the same amount of this one, which is our first term. So we would do f of x equals 5 plus our common difference, which our common difference in this case is the 4. Okay? So that goes here. So then plus 4 times x minus 1. And then you can multiply that out and simplify. So it would be 5 plus 4x minus 4, and then your 5 and your 4 simplify, so it would be 4x plus 1. Okay? Now, if you go to the next page, again, we still know this is the same one, so we know that this is linear, and our equation has the highest power of 1. Okay? This is the one that we've been looking at this year with me, is the f of x equals mx plus b. The m is the common difference or the first difference, and the b is the y-intercept or the f of 0. So this is a second way that we could do it, right? We still have that we're going up by 4 each time, right? So then here, when we write our explicit equation, we would have that we've got the m, which is 4x, f of x equals 4x, and then our 0th term. So if we were finding the 0th term here, that means if we were adding 4 going this direction, that means I would subtract 4. So if there were 5 in this one, that would mean that I would subtract 4 so that figure 0, there would be 1, right? So then I'm going to do plus 1. Okay? So again, this first difference or common difference matches the m, and then your y-intercept or your f of 0 matches the b. Okay? So if we go back up, oh, I forgot to put linear here. If we look at the next one, now notice on here that the thing that's changing is that we've got 1, and then this is 4, and then this is 9. So I'm changing, this is a 1 by 1 in the inside. This is a 2 by 2 on the inside and a 3 by 3 on the inside. Right? So what happens if we look at the numbers, we've got 5, 8, and 13. Right? So here I'm adding 3, then I'm adding 5, which since they're not the same, it's not going to be linear. So because our square is growing, or if you notice, we're changing both the length and the width, right? That would be an area kind of thing, which goes with quadratic. So this function is quadratic. Okay? So we have 2 dimensions that are changing. Or you can think, again, the second difference is the same. Okay. Now, this way was kind of how we had looked at getting the patterns. So here we're looking at the length times the width and then plus or minus anything that's extra. So in this case, we would find this area, and then we've got these 4 extra. Okay. So here we would have f of x equals, now notice from this figure to this number, those were matching. So whatever the figure number is, so I'm going to call that x, squared, because it's times by itself, and then we added 4. Okay? So the 4 is matching these four right here that we had extra. That's this part here. Okay. And then our length times our width is matching the yellow portion, which is the x times x.
So if we look at the other way that we can look at it, I filled out this part that we had already done. So we've got the numbers, so we know that this is quadratic. And we know that quadratic equations has a highest power of 2. So basically an x squared. Now sometimes the x squared can be written as x times x plus a number, or you could have it as x plus a number times x plus a number. Okay, that's an important distinction. You just have to do a little bit of math to see the x times the x is x squared and the x times the x is x squared. So that's an important distinction to make. Okay. So we also have the way that I have showed you, where you have ax squared plus bx plus c, where the a is the second difference divided by 2, the c is the y-intercept or f of 0, and then the b is something that you have to solve for after you've found your, or using the values that you have either in a table or a diagram or whatever. So if we start there, notice that our second difference here is 2, right? Because we had 5 here, 8 here, 13 here. So these are 3 apart, these are 5 apart, and then those are 2 apart, right? So then when those are 2 apart, that means that our a value is going to be 2 divided by 2, which is 1. Now our c value we can find by looking at our figure. So here we were adding 3, right? So remember that we're adding 2 each time. So if we're undoing adding 2 from here to here, I would be adding 2 as I'm going this direction, but if I'm going backwards, I would be subtracting 2. So if I subtract 2 from 3, that gives me 1, right? So that means I went up 1 from figure 0 to figure 1, but we're going backwards, so I need to go from figure 1, so I'm going to subtract 1. So if I subtract 1, that gives me 4. Okay? So that means that figure 0 is 4. You also could have made a table and done figure 1, 2, 3, so you've got 5, 8, 13, this is going up by 3, this is going up by 5, this is going up by 2, so that means that this would be going up by 1, so then I go backwards of going up by 1, which is going down by 1, so then that gives me 4 for 0. Both of those are fine ways to find that. So we know that our f of 0 is 4, so that as our y-intercept is 4, so our c value is 4. So now we can start writing our equation. So we've got ax squared, so a is 1, so just x squared plus bx plus 4 equals our f of x. But we need to find out what b is. So we're going to use the information that we have. So we can either pull it from the table or pull it from the diagram. So we need figure 2 or figure 3, it doesn't matter which one. So if we pick figure 3, that means if I want to find f of 3, I would use 3 squared plus b times 3 plus 4, right? So, but we know f of 3 is 13, right? So we know f of 3 is 13, so we're going to replace the f of 3 with 13 equals 9, because 3 squared is 9, plus 3b plus 4. So then when I'm going to move over here a little bit. So we've got 13 equals, and then the 9 and the 4 are 13, so 13 plus 3b. So I'm going to subtract the 13. So then that leaves us with 0 equals 3b, so then b is 0. So then our equation turns into f of x equals 1x squared plus 0x plus 4, which we can just simplify to x squared plus 4, which is, notice, the exact same thing that we had up here. So either way, you'll get the same equation. Okay? So I'm just going to highlight that we got this 2 value from this 2 value here. So for now you can't. Oh, there we go. Yeah, that makes it more visible. That's weird. So that's our quadratic. So if we look at the next one, okay, our next one is a pattern that we've not looked at visually, at least not this year. So notice here that we've got 1 in each one of these, and then we've got 2 in each one of these, and then we've got 4 in each one of these. So each time the parts of the X looking thing get doubled, right? So we're doubling each part. Okay. It may be a little less obvious that this is exponential by the figure, but you could write, we've got 5 in this first figure, 10 in the second figure, and then 20 in the third one. So figure 1 is 5, figure 2 is 10, figure 3 is 20. And then it may be easier for you to see that we're timesing by 2 and timesing by 2. So then that means that we have a common ratio, so then we know that this is exponential. So your exponential equations have a variable in the exponent. Okay, so linear has the highest power of 1. Quadratic has the highest power of 2, but sometimes it looks like one of these options. And then for your exponential, it has your variable in the exponent. Now, unlike the previous two, there's not two kinds of formats for you to find your exponential equation, so we only need to look at it once. So you can leave one of them blank or recopy the same thing on the one of the pages. And so what we have here is that we have where we've got the common ratio is the R part, okay? And then we are using the first term as well. So our first term in this case is what we have in figure 1, which is 5, right? And then we're just going to write this out, and notice that in our equation, in the exponent, it's written as x minus 1. Okay, that's just part of the formula that we have. So we have f of x equals the first term, which is 5, times by the common ratio, which is 2, to the x minus 1. Okay? And then that becomes our equation for our explicit function for the exponential. Okay? And that is a wrap-up of what we have been learning.